Hi guys, this is Mrs. Mooney, and this video is about defining and evaluating logarithmic functions. What if I said 2 squared equals 4? You know that, right? And if I said 2 to the third, you would know, well, that's 8. But what if I said 2 to the x equals 6? I don't know what x is. And there's not a perfect something that I can raise to that will give me 6. But what I can do is say I know 6 is between 4 and 8. So therefore, x has to be between 2 and 3. And I can narrow it down that way. But I can use a logarithm to actually figure out exactly what x is supposed to be to where I can raise 2 to that number and get 6. So here is going to be the basic premise of logarithms, the thing that you really need to know. If I take a base, a number b, and I raise it to an exponent e, equals a number, so base to an exponent equals a number, then log with a base of b of the number is equal to the exponent. So a lot of people look at this and they say, okay, well, b is your base. It's always your base. It's your base when you have a power, it's a base of your log. So that number stays the same thing. And then your e and your n just trade places, right? So you could memorize it by knowing, okay, well, the e and the n trade places, the exponent and the answer. Or some people look at this and they call it Ben and Benny. See, b to the e equals n, Ben, and b, log base b of n equals e, Benny. If that helps you remember which is which, then use Ben and Benny. Either one is fine with me. Or, come up with your own cute way of learning it. But you really, 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 really have to know that log base b of n equals e. Okay, here are some examples. I gave you some exponents, and I'm going to ask you, rewrite these in logarithmic form. So I said 2 to the 4th equals 16. If I rewrite it in log form, I'm going to say log, the base is 2, and then I just switch the 4 and the 16. So log base 2 of 16 equals 4. So on this one, I'd say log base 10, which you don't have to write the 10 if it's log base 10, but we'll talk about that later, of 10 equals 1. Another thing you can think about is it makes a circle, that, like that. So we could say log base 3 of 1 equals 0. And here we can say log base 1/5. And please, when you're writing your base, make sure you write it kind of slightly below and smaller than the word log. That way it's very clear which is the base and which is the number. So log base 1/5 of 5 equals -1. So yeah, these two numbers should be different sizes and in different places. Make it clear. All right, let's do just a few more examples. Now we're going to go the other direction and rewrite in exponential form. So our base here, 2/3, raised to the -1 power, and make sure you put it in parentheses because it's all raised to the -1 power, not just the 2, equals 3/2. And we know that's true because that just means take the reciprocal. All right, next one, base is 3, exponent is 3, and the number is 27. 3 to the 3rd is 27. All right, look at this one. Base is 7. Exponent is 0. Number it equals, anything to the 0 power is 1. All right, so now that you understand how logarithms work, let's try evaluating some without using a calculator. All right, I'm going to evaluate log base 2 of 8. And I have no idea how to do a log base 2 of 8, except what I do know is if that equaled a number, 2 to the number would equal 8. So I'm going to write that. 2 to the number equals 8. And then I can think about it and say, well, I know that 2 to the 3rd power equals 8. So therefore, my number must be 3. So log base 2 of 8 equals 3. All right, log base 10 of 1 over 1,000. well, I can think of this as 10 to the what number would give me 1 over 1,000. And then I can think, well, 1 over, I'm going to need a negative number. And then if I raised 10 to the third, I'd get 1,000. So negative third, I would get 1 over 1,000. So log base 10 of 1 over 1,000 equals negative 3. Okay, log base 4 of 2. So I'm saying 4 to what number would give me 2? I don't know. I can't raise 4 to something and get 2, but yes, you can because the square root of 4 is 2. So if I raised 4 to the 1/2 power, that's taking the square root of 4, that would give me 2. So therefore my n is the 1/2. So you have to think about negative exponents and you have to think about rational exponents, all of those things that we've already learned. Here are some more examples. Log base 5 of 1. So I say, well, 5 to the what power gives me 1. And I know that anything to the 0 power is 1, therefore my n has to be 0. Little trick, any log, with any base of 1 is always going to be 0 because you have to raise something to the 0 power in order to get 1. We have a math competition in our Mu Alpha Theta Club. It's called the Log 1 competition. And the reason that it's called Log 1 is because it's free. Get it? It doesn't cost anything. Yay, isn't that cute? All right, let's look at this next one. 1/4 raised to what power would give me 256. So these are going to get kind of tough like this, but you can do these without a calculator. I know that 4 to the 4th is 256. So if I took 1/4 and I raised it to the negative 4, then I would have the reciprocal, right? So 1/4 to the 4th would be 1 over 256. So if I make it negative 4, then I do get the actual 256. So I have my reciprocal power here. All right, log base 8 of 4. 8 to the what power gives me 4? All right, this one's tricky because I can't raise 8 to anything and get 4 directly. 4 is not a root of 8, it's not a power of 8, but 8 and 4 can be changed to have the same base. So just like when we were doing the half-life problems and we had to change our bases to match to be 1/2, 8 is 2 to the 3rd, and then you put your n along there with it, and 4 is 2 to the 2nd. So now I can figure out what n is because I can say 3n equals 2, n equals 2/3. If I raised 8 to the 2/3 power, I'd be taking the cubed root of 8, which is 2, and then squaring it and getting 4. So this is one of the trickier, tougher ones that I might throw at you on the test. You have to be able to change them to have like bases. All right, and then this last one, log base 3 of negative 1. So 3 to the what is negative 1. And I can't think of anything that I could raise 3 to get negative 1. I can't take a root of 3 and get negative 1. I can't make them have like bases. And really, if you think about it, if you graphed 3 to the x, it would be an exponential growth problem with an asymptote at y equals 0 and going up. So if that's at 0, will it ever equal negative 1? And the answer is no. That 3 to the n power will never cross negative 1. So this is not possible. We have a whole bunch of logarithms that are undefined. Because they just can't happen. All right. Okay, now, a couple things I want to share with you. The common logarithm and the natural logarithm. Those are two very special ones. The common logarithm is log base 10. And so, just like if I were to say the square root, I would have put this symbol. And you don't have to write the little 2 there. You just know that this symbol means square root. If I wrote the word log with no base, then I would understand that that base is 10. Okay? So if there's no base written, then you know it's supposed to be log base 10. And there's a button on your calculator that will do log base 10. It's over there on the left. It says LOG, really big, and that would be log base 10. Now the natural logarithm is log base E, We learned all about e in the last lesson. E is we called it the natural base. That's because it's the base of the natural log. So log base e is written as ln, and there's a button for that on your calculator too. It's right below the log button. So when you see ln, they're not going to write a little e on there. Sometimes it helps if you write a little e just because it makes us visually see it there, but you don't have to write it there. So log base e, the natural logarithm, is ln. The next topic we need to discuss is inverses, and we've learned all about exponential functions, and we've learned about logarithmic functions, log base a of x. Those would be inverses. If you switched x and y and solve for y, like that. If you switched x and y and solve for y, those would be our inverses. So, we could verify it, right? Just like I asked you on the last test, verify. If I were to take log base a of a to the x, well, I should get x, right? A to the what is a to the x? Well, our what has to be x. So log base a of a to the x is equal to x. If I did a raised to the log base a of x, then I would have to think, well, how do I figure out what x is? And that's just going to be x, because if I were to rewrite this as a logarithm, log base a of something equals my exponent, log base a of x, then obviously my something has to be x. So it verifies. A to the x and log base a of x are inverses. So here's an example problem. I might ask you to find the inverse. Find the inverse of y equals 8 to the x. You would switch x and y. X equals 8 to the y. And then we'd have to solve for y. And in order to get your exponent down, we have to write it as a logarithm. We'd say log base x, 8, log base 8, because this is our b. Even though I've written it in a different format this time, the base with the power is always the base. And then of x equals our exponent y. So the inverse of y equals 8 to the x is y equals log base 8 of x. Or let's find the inverse of y equals the natural log of x minus 4. I don't know why, but I like to use a cursive L on my natural log, maybe so it doesn't look like a 1. All right, what I'm going to do is imagine this little e here. All right, let's rewrite this. X equals the natural log of y minus 4. So I know my base is e. The base of any natural log is e. And then the power is x. And then that equals what I'm taking the log of, in this case, y minus 4. So if I wanted to get y by itself, I would have to add 4 to the other side. Y equals e to the x, and then the plus 4 is down here. Y equals e to the x plus 4. So that would be my inverse. All right, one more example of finding the inverse. This one looks exactly like the one we just did, except the one we just did had parentheses around the x minus 4. And this one is not going to have parentheses around the x minus 4, because I want to show you how important those parentheses are. All right, first we'll switch x and y. X equals the natural log of y minus 4. And then when we rewrite it from logarithm to exponential, before you can go from here, we have to make sure that the natural log is isolated, or any log. The log is isolated. That has to be by itself. So we have to add 4 to the other side first. We need x plus 4 equals the natural log of y. That has to be isolated. Then we can take, okay, our base is e. We're going to raise it to this entire other side, e to the x plus 4 equals y. So our inverse, y equals, or y to the negative 1 power equals e to the x plus 4. This time our x plus 4, our plus 4 is up in the exponent, whereas in the last problem it was down outside of the exponent. So you guys Make sure you're paying attention to whether we have parentheses or not. You always want to isolate the logarithm before you find the inverse. So that's it for our logarithms. Here's your fun joke. I hope you find it as excitingly lame as I do.